was kind of how you thought about it before, how the world thought about DNA at the time, and the process that you went through. And I know you had like a eureka moment, on that that changed the way that you thought about it and the way that the world thought about it and was eventually recognized. But could you take me through, the transition?
Well, the world and I were alike in the sense that we did not, until I had this realization that you could actually amplify it, people weren't looking for a way to make more DNA. They just sort of gotten into, this is about 1983, it was pretty clear that DNA was always going to be the least easily obtained of the things that were involved in a DNA type experiment. That was going to be the hardest one, a specific DNA sequence particularly. Whereas like organisms usually had like 5 or 10% of DNA in them, but not of any particular sequence. And so a whole bunch of techniques had been developed, cloning was one of them, to deal with the fact that to study DNA, you'd really like to have a lot of a particular sequence of it, one of them. And I was trying to figure out, I knew that was true, but I didn't know how, had not thought of a good way to do it. But I was trying to do something else, which was just to determine the sequence at a particular spot. But I was also, at the same time, writing computer programs. Which most,
I love this.
Most molecular biologists weren't, right? So if you write computer programs, you realize a reiterative loop is really an important concept in writing computer programs. And yet, I mean, most molecular biologists probably didn't know what that meant. But I had that in my mind. I said, if you can figure out something that can get you into a reiterative loop that does something for you, which I had figured. So when I first saw the fact that if I do this thing over and over again, it will double. I mean, it will double the amount of DNA in between the two particular sequences every single time. And so 20 times means about 1 million times. And 30 times means 1 billion. And that's about how many nucleotides there are in the whole DNA, human DNA. And so I could take this process. I guess you know how that process works now. It's just a couple of things. I was working in a laboratory that would synthesize little pieces of little oligonucleotides or little short pieces of DNA, so I had plenty of those. And I had plenty of DNA. So I didn't have to buy anything new, actually, to go test this thing out once I thought of it while I was driving my car, which is always a good thing to do when you're thinking about new things.
Better than texting people and stuff like that?
Yeah, I think driving a car, it keeps your hands busy, and it keeps you sort of from drifting on. You have some part of your head that's still available for thinking, but you don't. It's like, for me, it's always been a good karma kind of thing to.
It's either the car or the shower. That's the place.
Being in the shower,
I'm more of a shower person than I am a driving person.
You can
maybe because I'm a worse driver.
Time. I mean, I would drive for about 3 hours at a time every weekend to go up to Mendocino. I had this little place up there, and so that was a great time to be thinking about what have I done this week and what am I going to do next week in the lab. And nobody would interrupt you when you were in the car. So that sort of popped out of it was neat, the fact that if I had not been writing computer programs, I think I wouldn't have recognized a loop right away and said, hey, that's a loop. You could index that thing, and you could do it over, and you don't have to do the third or the fourth cycles of a loop. You just write down n is equal to n plus 1, and then it goes again. And now, so you could do that same thing in a laboratory, in an automated machine.
Well, even after you had done that, from what I had read, that not a lot of people believed it right off.
Well, people don't believe things usually for the right reasons, And the reason they didn't believe this was because of the fantastic result of it, not because any one of the steps was unlikely to work. Because the reason they had employed me at CETUS in the first place was to make oligonucleotides that would, in fact, be extendable on a DNA template. And I was saying, well, here's another way of doing it. And you're extending it on 2 at the same time, but you're doing it with the same enzyme. And what you can do once, you can do twice, and you can do it 3 times, and so forth. I wasn't asking for anything new. It shouldn't have been, this will not work because if it does, it'll put my lab out of business. That was the way that a lot of people looked at it. Because
this can't work. If it works, I'm in trouble.
If this works, what the hell am I going to do? Why do we need to clone DNA? If I can just, in one afternoon, I can amplify it all up and do it without cloning it, without, the smells of bacteria or their spells. And
well,
I think that was the real resistance to it. See, this was the result of it will be this. And therefore, the way it works must be wrong. That's the way a lot of people make their decisions about things based on those kind of, and they do that unconsciously probably. They don't realize they're just responding to something that's not got anything to do with what they're talking about.
That's a good thing to know. This also had implications pretty quickly at the speed at which you could run tests and other things, didn't it?
Well, yeah. I mean, it took. I think we had just finished cloning a gene at CETUS that took 40 people 6 months. And I chose that as one of the little models I was going to show. I can do that in one afternoon by myself now because I know the sequences at the ends. So
and some of these tests for things like sickle cell anemia and things
it made all that stuff work. It made that work, and then it turned into all the, the DNA evidence kind of thing, and the fact that you can trace the DNA in all kind of organisms back and watch the, you got a dinosaur around here somewhere, and you tell it has something to do. I don't know if we've got the whole sequence of dinosaurs yet, but we probably will.
Well, I think I saw it in a movie,
yeah. Well, they took pieces
Jurassic Park
it.
certainly thought that we could do it, so we must be able to do it.
Pieces of it and build it on a frog scaffolding, I think is what they use. We'd probably use a chicken today.
So you didn't stop there. Obviously, your career, went in a bunch of different directions.
Well, I guess you don't get to decide to stop. If you're, I didn't ever decide to start. So, no, I haven't stopped there. The thing I've been working on with Charlie there for a couple of years with Charlie, but for about 10 years before that was totally different and has to do with trying to come up with a new method. I come up with the method already, but it's making drugs that will be effective against all the bacteria that are now shaking off the hold that our antibiotics had on them. And this new method it's a very empirical kind of thing where you find a site, some kind of an interesting feature on an exterior protein on some bacteria that's giving you a lot of trouble, like say Staphylococcus aureus right now is a good target, and you find a unique thing, something on the outside of that you can model with a little peptide because it's a part of a protein, and you make a peptide synthetically, and then you select using that peptide, you select from a mixture that contains maybe 10 to the 11th different DNA sequences that you can make now on a machine easily. And you only get one molecule of each one, but you can make about 10 to the 11th sequences. And you now select from those ones that will bind to the site that you have selected on the organism, or to the model of it that a peptide is. And then you do PCR on that one molecule, and you amplify it up to where you have now enough of them to be able to read the sequence of it. And from that, you can synthesize it in large amounts. And now that becomes a specific little label that you can, if you swallowed it, and it was stabilized so that it wouldn't go away in your cells, in your intercellular fluid, if you staph it, then that thing will attach itself to, like, say, if you've made it to a protein on Staph aureus, that'll attach to Staph aureus if Staph is in your body. Now, if you chemically attach to the DNA sequence, that kind of DNA sequence is called an aptamer. Now, it has something to do with fitting, because the sequence of that aptamer fits onto some molecule that you've chosen for it to fit. And so if you now attach to that aptamer a little label that is something you're already very immune to, you have a lot of immune, like molecules, like antibodies to this other molecule. You attach that molecule to this. You've now attached that molecule that you're already immune to something that will grab onto the staph, and so you become immune to the staph, and that's how the system sort of works. And so we're working out the ramification. It's not as easy as doing PCR was, because you got to use animals and diseases and people that know about diseases and all that kind of stuff. So we're having a fine time finding collaborators around the world that'll help us do that. But it's working, and it's a simple idea. Thank you. So is marriage. So the thing has worked in lots of cases, and now we're sort of pursuing it in a commercial sense, but we'll get it.
Didn't you have some success with anthrax there? Yeah,
we did. We cured anthrax with some people that we didn't, because I won't come near anthrax. And
neither
but they
does
had
your
a
wife,
lab
I'm sure.
down at Brooks Air Force Base that we collaborated with these guys that had been working on anthrax for quite a while, and it cured anthrax 100%. Which is better than 40%, which is the numbers you get if you use like penicillin, kind of like Cipro is the drug of choice there. But if you get anthrax inhalationally and you know you've got it and you give yourself this drug, you get a 40% chance. And this, with our drug, it's 100%. So it's better. You would choose our drug. And but you're not going to get anthrax. It's just, there's a whole lot of people in the world still that are fighting World War II still. And one of the things that we ended World War II on note was, we might want to poison our enemies with biological molecules or either with organisms. And we really aren't going to do that. But there's a lot of government money available to do those kind of things, to defend against them. And that's how we ended up with anthrax. I don't see a lot of anthrax, What's that?
Did they fund your research?
Yeah, the research down at Brooks was already being funded. Uh-huh. So we just went and I said, why don't you use this method? And we supplied them with the DNA. The same guy that actually brought a DNA synthesizer over to my lab when I was working at CETUS, Ron Cook, who has a company called BioSearch. See, we were making before I invented PCR, I was making chemically oligonucleotides. And Ron was a friend of mine who had tried to make a machine that would do it. And he finally got one that worked. He brought it into my lab, leaving me with nothing to do. And so I invented PCR, which improved the oligonucleotide business by about 1 million-fold, which Ron was in the oligonucleotide business, so it was good. They didn't need to sell people machines anymore. But
so was Ron happy about that?
Yeah, he was happy because he sold them the oligonucleotides instead.
Oh, good. That's great. So obviously a lot of people here are computer scientists, and I'm interested in your, how you think the ideas of computer science, computation, large-scale systems. I mean, do you think if I gave you 100,000 machines, do you think that would help you, or do you think that matters? Do you think it's more?
100,000 machines. What kind of machines?
Other computers and stuff like that. I mean, is there a computational element to what you're doing?
I'll tell you, like, when this is something that I do this. I mean, there are people that do it with computers, but I do it with computers at the level of, say, if somebody's got an X-ray structure, a chemical, the absolute X-ray structure of some protein that's on the surface, say, of something like Pseudomonas aeruginosa, which is another organism that we have to worry about because it infects the lungs of humans that are compromised in certain ways, and it's also developed immunity to our, resistance to our antibiotics. So the way I use computers in there is like you go to a program that's like on the net already where people have the structural details of, say, surface proteins from Pseudomonas aeruginosa. You just look that up. And there are cute little programs available now where, you reach in there and grab the molecule and you can turn it and rotate it whatever you want to and stuff. And one of them that I just recently discovered that I really like, and then you can point at, you say, okay, that little piece sticking out right there, that little loop, that looks like a piece of that protein that's on the surface of this molecule, of this bacteria, that would be accessible from the surface, I mean, from out in the liquid. And it's sticking out. So you know that it's from somebody writing a really cool computer program that takes these little numbers and turns them into a picture of the thing that you can get in there and manipulate. I just love that thing. It's like I can say, all right, let's grab that little loop and turn it around. And I say, does that look available? Yeah, it does. You know, and it's something that I know there's a lot of computer programming involved in that, but I don't have to do that because I've already got the program there. But it means I can easily pick a substance or something on the surface of a protein that it says that that's on the surface of the bacteria that you don't like. That's how I pick them. And it's like, I mean, you could probably write a program to replace me there, but it's just the interface between the X-ray structural data and the user, like me, has been so well refined now by computer programmers that I can just, you know, I can do what would, it's like, it's so much faster if you can see something and you can move it to sort of pick through it and say, here's a good site. And you don't even know all the time. I don't know if I had to write down all the things I was looking for a site that would be cool. I don't even have a nice little checklist. I just sort of do it intuitively. It's because somebody has designed a really cool program that somebody like me that can just reach in and start playing with molecules. They do that for a lot of things now. I'm not just the things that I'm working on, but it's a really, I mean, I really appreciate that whole area of like visualizing and then allowing me to actually manipulate, like moving, to take two molecules and stick them to, you know, push them together in a computer. I mean, they have things that you can do that now. And it's really an incredible amount of like computation that's going on in there to do that. But it's stuff that I don't even have to know what it is. I just have this little molecule here, and I take this, stick this molecule, and it doesn't fit anywhere on it, you know. It's really a kind of, it's very, I don't know how many people in computer graphics it took to do all that, but they've really, I think it's been fun for a number of people because they've definitely made a very good sort of interface between chemists and the chemicals that they work with. And it's in, I mean, those guys probably don't know much about the chemistry at all, but they don't have to. I mean, but they've made this really cool thing. I appreciate that. If any of you guys did it.
There's probably a few people that have done visualizations once or twice here, no doubt about that. So what do you, if this is successful, if your current effort, which obviously seems like the hardest, more difficult thing that you've done, probably harder than PCR in lots of different dimensions.
Much harder.
But what do you think the future of our ability to basically, you know, get rid of some of these really horrible diseases?
I think it's there. I mean, the idea here is that you really don't need to poison the organism. You just need to reveal it to an immunity that you already have against something else, right? You turn it in, basically. You fool your own immune system in a way, but you're by having this kind of like control at the molecular level of things, you can put your finger in there where you're not supposed to, and you can mess around with it and you can improve it, because your immune system is amazing that it works at all. But with us directing it, it'll go a lot farther. And things like, there's all kinds of immunity problems that people have, but the biggest one, I mean, what I'm trying to approach right now is just, like if you get exposed to something, a lot of times you don't make an immune response just to everything. So you need to be in the executive seat, in a sense, and say, we want to kill this thing right now, today, you know, and I can make chemicals that are directions for you to do that with. But I need to have that kind of information, the input from like knowing this bacteria that you don't like happens to have this structure on the outside of it, and you can use that as a way of pointing that bacteria out to the immune system. The immune system has got a lot of functions. It's got a whole lot of tanks and a lot of serious equipment that's going to waste because it was made for one disease, and then once that disease is wiped out, it's not useful anymore. You can't take an immune response and retool it, and that's what this system that we're working on does. It takes immune responses that you already have and that are more or less they're useful to you, but they can be much more so if you can go in and change the guts of them, in a sense, to say take the guns and point them at this thing, instead of saying the way the immune system works now. If you get some new organism that you're supposed to be immune to, you have to say, now I have to raise a whole new army, and I have to train it, and I have to do, rather than just saying ship a few of these guys over here and tell them to point their weapons at that thing. That'll make a big change in the way we become immune to things. Because if we don't have to go through the process of becoming immune to every new threat, we just use an immunity that we already have. That'll make a big difference. Because it costs you a lot of energy to make a new immune response, and every time you do, you have collateral damage, because an immune response is not absolutely specific. So we're trying to, there's a whole bunch of different problems that
are there some kinds of things that it will work better or worse on? Are there some things that are really, really resistant to the new approach, and some that you think are going to be easy?
The things, nothing right now has shown that it's resistant to it. But the thing about being resistant to antibiotics is there's a reason for how come, bacteria learn how to avoid them. And this doesn't have that element, because they haven't learned how to avoid your whole immune system. They just learned how to avoid this one little antibiotic. This is sort of like going back behind the curtain of the immune system and sticking your hands back through and say, okay, now we're going to change some settings. And so it's not something that the bacteria is going to be expecting. It's like
the vision I get in my mind is the guns are trained to look for other guns, and you're painting guns on all these other
exactly. That's what you're doing, is you're painting little targets on things that you would like your immune system to take care of. And your immune system is quite capable of doing it. As soon as it figures out that this is a target,
right?
It's
trained.
It's not
100%.
missing any power. It has all the power you could possibly trust some system to have in your body. You wouldn't want to give it any more. You certainly wouldn't want to have the immune system be able to do this by itself. You wouldn't want to have it change an immunity, because as a new immunity is developed, there's all kind of checks and balances to make sure you don't become immune to your own heart or something. Right? So we're going beyond what the immune system is capable of doing and what you would trust your immune system to do. Because we're saying we already know what the structure is of this thing, and we're going to make something that goes to get that, and we'll make the decisions that otherwise were made by sort of like rote, or by trial and error kind of things in the immune system.
Well, this has got to excite you, because there's so many things like cancer and things like that we end up having poison bodies for, that you think.
Thinking about cancer more than me.
You are.
I like to start with simple shit like bacteria, but it's there. I mean, the immune system is what keeps you from having cancer in the first place.
Yeah.
So it's possible this will open up that whole area.
Wow, that's fantastic. So stepping back a little bit, there's been a lot of talk on the decline of math and sciences, and the decline of our ability to do math and sciences as a country and things like that. And you've obviously got a lot of experience, and math and science has been really central to you. So how do you think from a global perspective on math and science education and research and development, dollars and things like that? It seems kind of strange that you have to go to the Defense Department for this particular research.
Well, if you read about...
By the way, we went to the Defense Department for the internet too, so
I'm reading a book right now about the Middle Ages and sort of how science sort of first got inserted into the world, and it was basically through military. I mean, there were always still military stuff going on. It's like you know, where the cool big machines like the trebuchet things, that was for blowing up people. I mean, smashing in their walls. I mean, I think the military always has that it's always oversupplied with the kind of stuff that scientifically minded people, engineering kind of scientific minded people need. So they just happen to have it. It's hard to explain to them what it is that they have sometimes. It's a weird thing that we're doing. We're dealing with that still today. It's getting government grants, right? And so it's easiest if you can explain it to them in the sense of like, some horrible country might use this against us, you know. So don't you want to be prepared?
So that argument is much better than, you know, solving, you know, all
it's
disease
much better than
in
saying,
the world.
yeah, there's a whole bunch of suffering people in the world. Well, screw them. I mean, we're just worried about whether they're going to drop stuff on Manhattan, you know, and what are we going to do about it? And fortunately, if you convince them, you don't have to. The military is totally convinced that some big country is going to drop like bacteria on us. So they're willing to fund that kind of thing, you know. But really, I mean, the purpose for that is to keep people from having all kind of horrible diseases.
Yeah, that's great. Well, it's good that there's a very positive side effect associated with that. So
it is. I mean, it doesn't come from the nicest places that humans have, but it definitely is a positive side effect.
Yeah, no, I'm willing to spend almost anybody's money for good things. So.
Yeah.
No problem there. So one of the things that I thought was interesting in the zeitgeist is just, you know, kind of innovation and thought and the way you think about problems and, you know, how you think differently about problems. And you know, one of the things that you talked about was kind of the incremental approach versus other approaches. I mean, I think the reason you've been successful is you've thought differently, but, you know.
Well, I do happen to, like, not really care where the idea goes. I mean, I'm not really trying to, when I'm starting to think about something, I think about it in the same way an engineer would, actually, which is more like, how do you fix this thing? I mean, what would you do? And I think that, also, I'm not really worried about, I don't know why, but I'm not really worried about what people might think of me. You know, it's been to my advantage to be that way. I don't know. It's very, I think, in our genes, in a sense, to like keep our head down. Like if you can think, I imagine a row of guys 2 million years ago walking across the savannas of northern Africa, like hunting and stuff, and you didn't want to stick your head up too high. You want to kind of get down behind the guy in front of you. And because you might get killed or eaten or whatever if you make a sort of a noise or like a spectacle of yourself. So we have this really strong kind of need to follow. And it's not terribly conscious, but keeping your head down below like the line of fire is it works its way up into like, what will you do as a professional scientist in terms of what are you going to work on this month, you know? And there's a whole lot of there's a real conservative sort of no, we can't do something that would be totally ridiculous that other people haven't done. You know, that's not. It's sort of like you want to do something that what people haven't done, but it's got to be sort of in the line of things that they have done. It can't go against, you know, the general concepts that are floating around in the field. And so I'm sort of a contrarian kind of a person, I guess. My mother gave me a little private room.
Is that true? Is he a contrarian kind of person? I believe we have firsthand evidence.
And I think it
that.
helps to have a few people like me around that just say, I don't like any of this, and here's a better way to do that one, something like that. And I think having had the opportunity to be an experimentalist at the age of 10, you know, was a handy thing to have. It taught me a certain amount of confidence in myself. And I mean, there's lots of people like me. There's not as many of them as there could be. There's
so let's follow
more.
up on that because you know, who are the people that influenced you? Who are the people that you look up to? I know you do a lot of reading and you like history.
I read mainly for like not who they are, but like what they're saying, I usually forget who they were. The thing that inspires me to do stuff is the stuff itself. You know, the fact that you can do experiments. You don't have to ask somebody, is it okay? Or what would happen if I did this? You just do it and find out. And I think I was just sort of, I was bred that way somehow. And I was always doing that. And I think that's, most scientists have something about that in them, but a lot of them pay a whole lot more attention to like the guys, like who's getting the most press attention or who's getting this or who, and what does Francis Collins think about this? You know, what would he fund this kind of thing? And I think I'm more driven by the facts.
Does that tie into the funding side too? Because I think the experts often control the funding.
Yeah, no. I find myself begging people for money.
Yeah, this is a strange thing. I mean, how can you be as successful as you've obviously been successful and have to beg for money that, with reviewers that have been a lot less successful? And I know in the computer science, there's some people I know that are as, have had the most contributions of anybody. I won't name names here, but they're begging for money in ways that it makes no sense to me.
I don't like it, but that's always the way it seems to be. I don't know. The guys, I mean, the people that control things, that run the big funding agencies and all that stuff, those people are not themselves personally terribly creative or reliable, even in a sense of producing things. And
so how would your peers look at you? I mean, do they come around, or do they still hate you from things that happened 20 years ago?
I mean, one of the nicer things they think about me is that I'm a lunatic. You know, but they have to admit that some of the things I've done have worked. You know, so but they don't have to admit that the next thing I'm going to work on is going to.
So you don't have to get any chits that you can play in the next round, huh?
Yeah, that is the truth. It's not. It must have been good luck before, you know. That's the way they look at it.
Blind luck.
Because not some crazy, guy like this was not going to do anything good. So, yeah, I would have thought, but now, I mean, I'm 65 years old, and I'm still working. You know, I would thought it'd be real easy to get funding. It takes somebody like Charlie coming across from London to like say, okay, we'll put a few bucks on this thing. But not everybody. I mean, we spent a long time with this idea, probably 10 years, I guess. I don't need any more. But I mean, we spent a long time trying to get somebody to fund it, and always getting money from, like, say, from DARPA. They were willing to put up money at first. But they, again, they have a military angle. Yeah.
It was funny you talked about the experimentalists, because I was talking to my daughter about this morning, because my dad and I laughed along to, this is, 20 years ago. There was a Dear Abby article, and the Dear Abby article was somebody wrote in and said, do you use less water in a shower or in a bath? And so Dear Abby consulted hundreds of experts, and then the experts said this, and my dad just looked at me and says, why don't you just put a stopper in? On it, take a shower, look at the amount of water, take a bath. But it's funny, people don't think that way.
I think that way.
I do too.
That was immediately my response to that. Put a stopper in the way of taking a shower.
Now you know.
Water, is that enough to take a bath in?
Oh yeah. So does the audience have any questions? Go ahead. Here, you want to use a microphone here?
There's a couple high-profile people in the biofield, and the other one I was thinking of was Craig Venter. How would you compare yourself to him in terms of the arcs of your career?
Well, Craig I like Craig, but I mean, it's in spite of the fact that my very first experience with him was down I think we were in Hilton Head, South Carolina, at a meeting. And after the meeting was over, a bunch of us decided to go skinny dipping out in the ocean out in front of this hotel where the meeting was at. And Craig decided it would be a good idea to steal our clothes. Because it was very embarrassing. Between the ocean and our rooms, where more clothes could have been found, was a big area outside, pond and a bar and a whole bunch of people, and it was pretty embarrassing to be sitting there thinking, where the hell are our clothes, you know? And so I asked some waiter, I said, did you see somebody take our clothes? You've been in this area? And he said, that guy over there in the hot tub is the guy that did it, and it was Craig. So I knew that he was not going to be trifled with, so I picked up a deck chair and I walked over there and held it over his head and I said, get us our clothes, and he got them. So that was the beginning of our relationship. It's gotten a lot milder.
Did it go uphill or downhill?
It's gotten milder, but he has a totally different style than I do, you know, and his is successful. In the sense that he knows how to raise a lot of money and get a lot of people and buy a lot of machines and set up a big industry kind of out of his personal plans, kind of like what he's going to do. Like he wants to sequence every piece of DNA on the planet. And I think that's kind of cool. I mean, he's a fanatic, you know, but he's different than me and more successful by far in terms of the amount of stuff he's done. But he hasn't done anything new. He's just done many, many times more sequencing kind of stuff than anybody else has. So I respect him, but everybody doesn't, you know. The same reason that everybody doesn't respect me, because I'm just a little too weird for them. And I think.
But have you stolen any clothes? That's the question.
I wouldn't have stolen any clothes.
So you spoke about this idea of painting targets on bacteria. Would that work for viruses as well?
Yeah, it works for viruses. We're one of the organisms. We were actually getting some pretty good data with influenza until our influenza lady moved to Minnesota. So while she's shut down, we're looking for another influenza person. But yeah, it'll work for anything that's. See, and the immune system deals with viruses. It deals with things like, say, influenza when it causes your cells to start making influenza viruses. It puts a lot of things on the surfaces of those cells that wouldn't normally be there, that the virus wants to put there because it makes it easier for it to do its stuff inside the cell. That's what you use as a target. You say any cell that's been co-opted by influenza is going to have these little things called M2E, which is a little target that we can simulate with like a nonapeptide. So if we because it makes these little holes in cells, and in order to do that, it has to put some of its proteins on there, and they're therefore susceptible to the immune system. So we just redirect an immunity to eat those cells. The immune system's a whole bunch of hungry cells, basically, that are not allowed to eat anything they find. They're only allowed to eat it if it's got a bunch of antibodies on it. That means this is for eating purposes here. And so that keeps them from eating other things. So we're putting those antibodies on there because we find out from the chemists what the flu puts on there, what's different about those cells now. So you don't actually kill the virus itself, you actually kill the cells that makes the virus.
Thanks for coming here. 10 or 15 years ago, you had some views on HIV and AIDS that were very controversial. So
they still are, yeah.
You know, where do you stand on
that?
Well,
what I've come to the conclusion over a long period of time, and a lot more study and reading than most people would sort of give me credit for, because they think, get out of my field, you know. They think it's their field, and that nobody else could possibly have anything to do about it. It's occurred to me, and I think the retroviruses are going to end up a lot of times being like this. The thing that causes AIDS is not a species of the retroviridae. It's the whole genus. And it's the way that there's some members of the genus that are much more effective at doing it than others, but it isn't caused by one, like HIV-1. That was that somebody sequenced that, and then they found, hey, every time we find this, every other patient is a slightly different sequence. And that never struck home in people like Bob Gallow's mind. That we're not dealing with a species here. We're dealing with, and if you look at the properties of the retrovirity, the genus to which the HIV virus belongs, the way it works is it goes in and it's a DNA thing. It like sticks its DNA into lymphocytes, and the DNA just sits in there until that lymphocyte starts to divide itself rapidly. And then the DNA starts making protein, or RNA and then protein, and then making particles that are infectious. And it's a cyclic kind of a phenomena. It goes around, it infects new cells, and it starts doing that. But it doesn't immediately start doing anything. It goes into the cell and waits until that cell starts to divide rapidly. So what that translates to in the immune system is that once a sequence, because those sequences mutate really fast, because reverse transcriptase is involved in their replication, and that makes mistakes at 100,000 times more often than like DNA polymerase does. So there's a real, that genus is very, very heterogeneous inside of it. And what's happening is you get a sequence that starts replicating itself. It makes some mistakes. It infects other cells. It sits there and waits. Most of the time, it's just a piece of DNA. It's ridiculous to fight it only at the time when it's proteins and it's infectious particles. That's what they do. I mean, all the retroviral drugs can only be direct. They only are effective against the RNA containing protein form of the disease, and they can only just do so much. They'll modify the rate at which it happens, but the real problem is that you've got lymphocytes that have all these sequences in them that are sitting there waiting to their good time. When the lymphocyte starts reproducing itself rapidly, they reproduce. When it's not, they don't. So you can't kill it by stopping it at the protein level. You can kill its action. You can stop it from taking action right now, but it's still got the DNA sequence in a bunch of lymphocytes. So until we figure out how to deal with that problem, I don't think we'll have a useful drug against any of the retroviral. They're coming up with new ones. There's new things that have been blamed on retroviruses. And the very first thing that people have to recognize when dealing with them, that they're dealing with they're not just dealing with one single thing. Like one sequence is not, just because you can only detect that one. See that, there aren't any nice tests for retrovirity in general. There aren't any tests. So you could give them to people and say, my God, people have got all kinds of retroviruses. But they only have a very specific test for the proteins that are involved in HIV. So they can tell you whether you got that, but they can't tell you whether you got a whole lot of related things. And that's really the difference between people that get sick and people that don't, is that people that get sick have a whole lot of different versions of the whole thing. This is my feeling about it, and it's not an unsupported kind of feeling. It's from just looking at the data. More and more data is coming forward that supports that idea that it's not just HIV as originally defined by Bob Gallo and Luc Montagnier. It's a whole bunch of things, and they're retroviral, but they don't have the same sequence. And just killing one particular little cluster of those guys is not going to stop the disease.
Well, great. I think we pretty much have run out of time here. I'd like to thank Kary very much for coming today.
Thank you all very much.